Hello everyone, this is Ollie Epsom. Welcome to the second in our series of lectures about aeronautical engineering. Today we're going to talk about rockets and rocket engines. This is a recording that I subsequently made from an earlier presentation that I made online a couple of weeks ago during the COVID-19 lockdown. I'm not in any way really an expert on rocket engines, but I hope I know enough about them to at least give an introduction to those who might not be familiar with them in any way at all. And hopefully this sort of fairly straightforward introduction will give you enough basic information that you can go and find out more detail if you want to. So with no further ado, let's get started. We're going to understand the need for rockets and rocket engines. We are going to look at the different types of rocket engines that are in existence, primarily the two main types, solid fuel and liquid fuel. We're going to look at the development of rockets and rocket engines up to recent years. And we're going to examine the principles of a multi-stage liquid fuel rocket engine, which is the most common type of engine used for standard space launches at the moment. There isn't going to be a great deal of extensive technical information in this, and I'm not going to be using equations or mathematics. It's something that I may do in later editions of these sorts of lectures if there's a demand for it. But at the moment, really, this is an introduction, and it's not supposed to tax your mathematical skills too much. So why do we need rocket engines? For a couple of reasons, really. The most sort of prominent one is that they are the only means which we can currently access space, especially Earth's orbit and especially low Earth's orbit, where there are many various satellites. There's the International Space Station, which you can see at the right-hand corner here, and geosynchronous orbit, which is much higher up, which is where things like GPS satellites live. We also need them for longer trips, sort of outside of Earth's orbit. So at the bottom left here, we can see a computer-generated image of a long-range space probe. There aren't that many of them in existence, and there aren't that many that have been launched, but it is a very important scientific endeavor. And again, rockets are the only way we can achieve that. We also use them in terrestrial applications, most notably, for example, guided missiles. Here's an old Soviet SA-2 type missile, which was an early surface-to-air missile, which was large, expensive, and fueled by a liquid-fueled motor, widely deployed in Vietnam and other theaters. And we use them for various special purpose applications. Here is a Martin Baker ejection sheet being tested. Now, those will use a solid fuel propellant that will be in the back of the seat, and when the charge is ignited, the seat is catapulted out of the aircraft. This is Martin Baker's test aircraft. As an aside, it's a very old Meteor test aircraft that they've fitted with essentially a detachable rear cockpit so that they can test the live ejection of a seat whilst the pilot returns to base. It's one of the oldest operating jet aircraft in the world, as far as I believe. But anyway, I digress. First thing we're going to look at is how do rockets work. It's relatively straightforward. Rockets work because of Newton's third law. Newton's third law states that for every action there is an equal and opposite reaction. What that means is if you push something one way, then the thing that it's connected to will want to go the other way. The most obvious example is a balloon. The air in the balloon rushes out of the bottom of the balloon, which propels the balloon and the remaining air in the opposite direction. A rocket is essentially a much more sophisticated balloon and works in the same way. What's pretty important is that it works in a vacuum. Rockets work because of Newton's third law. They don't work because the gas rushing out of the back of the rocket is somehow pushing on the surrounding atmosphere. That's not how they work. Rockets work best in a vacuum, which is why they work well in space and is why they are currently essentially the only way to maneuver in space. There are other methods, but you could class them as rockets in some other way as well. All speed in space is relative. What that means is that space is not a grid in which you have fixed objects relative to this spatial grid. Essentially, everything in space is moving relative to everything else. There is no sort of fixed point. And the reason I mention that is because a rocket in space will keep accelerating until it has no more fuel. It will go faster and faster and faster until there is no fuel, because it's not accelerating essentially relative to a fixed inertial plane. And the key point is that rockets need a lot of fuel. So as we'll see in a minute, most of the weight of a rocket is fuel. And this is really a key reason why rockets are expensive and complex machines in their own right, and why wider access to space doesn't exist at the moment. Okay, as I just said, we're going to need a lot of fuel to get a rocket into space. So typically about 90% of the weight of the rocket is fuel. So here we have a Delta Heavy type rocket lifting off, and 90% of its entire mass is fuel. In this case, it's liquid fuel. Could be solid fuel, but we'll see more about that later. 6% of it is the structure. Now that is the rockets, the rocket engines, the fuel tanks, the control equipment, the electrics, and so on, is all the structure of the rocket. So again, there's a lot of engineering that goes into getting the weight of that structure down as low as possible, and there's quite a few tricks that are needed to do it. In some cases, for example, fuel tanks might collapse if they became depressurized because they're not built heavily enough to sustain their own mass unless they're full of fuel. Less than 4% is the payload. So that means the cargo, the control systems, the astronauts, whatever it is you've got up here in the payload bay is less than 4% of the total mass of the rocket. What that means is if you want to put 4 kilograms into space, you're going to need about 96 kilograms of fuel and equipment in order to do that. Now, in actual fact, you probably wouldn't be able to put 4 kilograms into space on its own because of scaling issues, but if it was that little, you'd probably need a lot more fuel and a lot more structure. But it does give you an indication of just how much stuff is needed to get not much into space, and why it is very expensive and difficult to do it, and why access to space is so heavily restricted. And this is one of the reasons, not the only reason, why rockets are very expensive, is because of how much fuel they need and how many engineering tricks you need to do to get the structure that light. There are other reasons rockets are very expensive as well. And as I said, here at the top of the rocket is the payload. Everything else is fuel and structure, and you launch it off and you never see it again. You don't get to use it again. It is a use once and throw away device. So it is not the most efficient machine in the world. However, it is at the moment the best we have. There's two main types of rocket engine, solid propellant and liquid propellant engines. I'm going to speak a little bit about both of them. Solid fuel engines are in many ways the simplest to understand. It is essentially a glorified firework. So in a solid fuel engine, you have some form of fuel and oxidizer combination that has been compacted into a solid form. So it's not gunpowder, which is what you'd have in a firework, because gunpowder burns too fast. It might be aluminium and some kind of oxidizer, for example, bonded in some resin. But the key point is that when that mixture is ignited, it starts to burn very quickly. It doesn't require external oxidizer, and it comes out the back of the rocket and off it goes. There's a number of advantages to solid fuel rockets. They are always ready to start because they can be stored fully fueled. This solid fuel is generally designed to be quite inert and quite safe, and it takes a very special ignition system to get it going. So it can be stored for quite a long time. That's particularly useful for things like missiles, where you might want to have them in a silo or on an aircraft wing for a long period of time before deploying them. They're simple and they're cheap because there isn't a lot of auxiliary equipment. You don't need a lot of pumps or refrigeration equipment to keep the fuel in place or move it into the engine. They're very basic. And as I said, they are ideal for missiles, and a lot of missiles do have solid fuel rockets, particularly short-range missiles, air-to-air missiles, surface-to-air missiles, that kind of thing. They do have some disadvantage though. It's impossible to control or stop them once ignited. What that means is once this thing is going, you don't have any control of the throttling. You can't throttle it, it just goes. You definitely can't stop it. So once it's started, it is burning until it's finished burning. Now, that isn't usually an issue for military missiles, which are unmanned and generally have one purpose. And generally, the idea with those is that they will get to their target as quickly as possible. But it is or can be a problem for more commercial rocketry. And they're not as powerful as the alternative form, which is liquid fuel, for many reasons, generally to do with the chemistry of the fuel itself. They are generally pretty powerful, but they're not as powerful. If you want an absolute maximum power you can have, then you're going to need a liquid-fueled rocket, and it's going to need to be burning hydrogen and oxygen. Here are some typical examples of solid fuel rockets. So as we said, the Martin Baker ejection seat under test here on the left has got a solid fuel rocket for many of the reasons we've just said. They're simple, they're cheap, and they can be left in that ejection seat, always ready to start at a moment's notice. The disadvantages aren't an issue. They're not trying to launch this poor pilot into space, so they don't need a lot of power, and they don't need to control the thrust. These rockets fire for a second or less, bang, off they go, and they'll burn out when they burn out. Here in the middle we have the space shuttle, which is decommissioned now, sadly. Now the space shuttle is one of the few examples, if not the only example I can think of, where solid fuel rockets were used for human spaceflight. It didn't work out particularly well, as some of you may know. The space shuttle had 2 solid fuel boosters, which is what makes all of the smoke and pollution that you can see here. It also had 3 liquid-fueled engines on the main shuttle, which we'll talk about later, and they basically emit a wake that you can't really see. Now, at liftoff, those boosters provided about 70% of the thrust that was available, but of course they could not be controlled. So once those things were ignited, those astronauts were at the mercy of the solid fuel booster gods, which, as you know, with the Challenger in 1986, were not smiling on them. On the right-hand side here, I've got a picture of a Sidewinder air-to-air missile. These missiles have been in service for a lot longer than you might think, sort of from the 50s onwards, and they obviously they've been updated over the years, but they were a very good fundamental design, which has allowed them to be updated. The engineers back then did a very good job building something simple, reliable, and relatively cheap, certainly for a military piece of equipment. And they obviously have a solid fuel rocket motor. Okay, so let's look at liquid-fueled rockets. Liquid-fueled rockets are conceptually relatively simple, but in practice, as we shall see, they can be very complicated. The key difference between a liquid-fueled rocket and a solid-fueled rocket is the separation of subsystems. So on a liquid-fueled rocket, you have the fuel stored separately from the rocket engine. It's not the same thing. You generally have a tank of some liquid fuel and a tank of liquid oxygen. The liquid fuel is most commonly either kerosene or liquid hydrogen, and there are advantages and disadvantages to both. Quite often, kerosene is used for the first stage engines and liquid hydrogen for subsequent stages, but that's a little bit more complex than what I want to get into today. The fuel is taken from the tanks by pumps, and when I say pumps, we are talking, as we shall see, gigantic pumps that have the power of jet engines. These are not, like a fish tank pump. And that fuel is pumped at enormously high rate into the engine itself, where it's combined, burned, and out the back it goes. Now, liquid engines are extremely powerful. They're the most powerful kind of rocket that we can build because they generally use very efficient chemical reactions. The mixing can be controlled precisely, they can be throttled, the nozzle can be controlled, and so on and so forth. So they're very powerful rockets. They're controllable. We can switch them on, we can switch them off, and we can throttle them. Now, it is true that many engines cannot be restarted because they haven't been designed to do that, but conceptually there's no reason why they can't, and many engines can be restarted in flight. They can, depending on fuel type, be very clean. As we saw in the preceding picture with the space shuttle, the liquid-fueled engines basically don't make any kind of visible smoke because essentially they're combining liquid oxygen and liquid hydrogen, and as you know, that results in water that is very clean. That is not always the case. You do get hypergolic type rockets like the Russian Proton, which sprays carcinogenic compounds over a wide area, but they're generally not used in the Western world. The disadvantages are they are very expensive because there's an awful lot of heavy engineering in these pumps, in the nozzles itself, in the tanks that hold the fuel. It needs very complex fueling infrastructure, not just to fuel these things, but to keep the fuel in place. So if we're using cryogenic fuels, that is to say fuels that are normally gases but have been cooled to very low temperature, such that they are in a liquid form, i.e. liquid oxygen and or liquid hydrogen, then we need to maintain that very low temperature of the fuel in the tanks. That takes additional infrastructure. For the same reason, it means that these things cannot usually be left for a long period of time fully fueled. That's not necessarily the case with all liquid fueled rocket engines, but it is generally the case with cryogenic rocket engines. And that means that you then have to defuel it if you have a launch failure, for example, or a cancelled launch sequence. And that requires additional infrastructure where you may have to pressurize the tanks, for example, to keep them inflated, because often the tanks will collapse if they are not under pressure internally because they've been built to such a lightweight design. There's a couple of examples of liquid-fueled rockets here. On the left, you can see a SpaceX Falcon 9 taking off, which is an excellent example of a modern liquid-fueled rocket. The guys at SpaceX have done some very clever things there. I'm not going to go into too much detail about it today, but if you wanted to read more about it, feel free, or ask me and I'll make a more in-depth video about it. On the right, as I said, here's a picture of the space shuttle. Now, this is at that point where the boosters have separated after a couple of minutes. You can actually see the explosive bolts have fired, and then there's a small jet that comes out of the top of the boosters to blow them away from the main shuttle. Now, the shuttle continues with its external fuel tank, which is foam coated. That's another story. And that foam coated external fuel tank is feeding oxygen and hydrogen into the space shuttle's three main engines, which are at the back, and they are running at full power in this photograph, but as discussed, they're just making a relatively invisible flame because the only thing that's coming out of them is water, and they were amongst the most powerful liquid fuel engines ever built. Actually, the space shuttle main engines, they were very sophisticated pieces of engineering in their own right, and deserve me to actually do a properly researched video on them at some point. The development of rockets has not exactly been smooth. Most of it has taken place in the last 70 years. In the 1200s in China, gunpowder in some form was developed, and there are many accounts from the day of fireworks, as we would call them today, being used. Now, they were mainly used for decoration or, celebrations. As far as we know, they weren't developed further into, for example, weaponry, and certainly not into any form of transportation. Nonetheless, the technology did exist in China, and there it stayed for a very long time. As in many cases, it was the British who decided that rockets would be a most useful way of killing people. Because if there's one thing that gets the British excited, it is new and exciting ways to kill people. And the first use of rocketry in warfare that I have been able to unearth was in 1807, when, for reasons that are long and complicated, Britain attacked Copenhagen with rockets and generally caused some mayhem. When I was actually giving this lecture online, there was a Danish guy who pointed out that notwithstanding the fact that Britain had burned Copenhagen with rockets, it was easier to get hold of fireworks in Denmark than it is in the UK, which is very true. It's also worth knowing that at some point Britain has invaded or bombarded pretty much every country on Earth, so there's nothing particularly unusual about it being Copenhagen. Liquid-fueled rockets were first developed in 1926 by Robert Goddard, who had this concept of using liquid as a controllable rocket engine. Very far-sighted man. There were also developments in Germany at about the same period, where they would also claim that one of the first liquid-fueled rockets was launched near the town of Dessau by an employee from the Junkers aircraft factory, and actually you can go there and see that as well. But it was round about the 1920s, 1930s that interest in rockets became more pronounced, particularly in Germany, particularly in Russia, and particularly in the United States of America, where very bright people made some quite considerable theoretical and occasionally practical advancements in the art. It was primarily World War II and mainly the Germans who sort of propelled, boom, boom, rocketry into something more like what we see today. Obviously, there were many people involved in the development of rocketry, and it wasn't just one or two engineers. However, two of the most prominent, the ones who probably had the biggest influence, were Wernher von Braun, who you see here on the right, and Sergei Korolev, who you see here on the left. Now, as in any instance, the personalities of these people were probably more important than their actual technical ability. These are people who were very good at pushing for what they wanted. In particular, von Braun, who really did stop at nothing, and I mean nothing, in order to ensure that he had sufficient funding from first the Germans and then the Americans to get what he wanted. I mean, he was a man who had a vision, and the vision was he wanted to build gigantic rockets. He, I would suggest, did not have a great deal in the way of a moral compass, as we shall see. Sergei Korolev was a much more, I would suggest, reasonable, solid engineering character. He had a lot of respect internally, at least towards the end. So Wernher von Braun was a German. He lived from 1912 to 1977. He was a committed card-carrying Nazi and was well known at the time and is well known now. Sergei Korolev was a little bit older. He lived from 1906 to 1966. He was a Russian. He had a pretty bad life, like a lot of Russians under the Stalinist regime. He was interned in a gulag and basically left to starve to death and or work to death, whichever happened first. I don't think they were too bothered. And he was pulled out of the gulag in order to resume what had up till then been his sort of pet project of rocketry. And this he did with a remarkable degree of success. And I would say that more than any one other person, he probably did do more than anyone else to develop what you might refer to as sort of useful spaceflight, as what we'll see in a bit. Von Braun developed rockets for the German army, most notably the V2 rocket, which was the first sort of successful mass-produced heavy liquid-fueled rocket. We'll look at that again in a bit. It was built in conditions of appalling slave labor. Thousands of people died making these things, more in fact than were killed by them being used as weapons. Von Braun, of course, claimed that he didn't have anything to do with that. He was merely, he was merely a paper guy. He wasn't interested in logistics. Of course, it was all nonsense. He knew exactly what was happening. He didn't care. After the German surrender, there was an operation by the Allies called Operation Paperclip, where they were scouring Germany for people and or engineering equipment that might be of use to the Allies in any subsequent confrontation with the Soviet Union. And they grabbed a load of the top German engineers and their equipment, so fighter jets, metallurgy, rocketry, engineers, and brought them back to America primarily. Von Braun was one of these people. Now, initially, he was put to work on rockets in America, so they tested his V2s, for example, in White Sands Missile Range and other locations. And, they pumped him for information, got what he knew, and essentially pensioned him off originally. There's a bit of a myth that the Americans kind of ignored his Nazi past, and I'm not sure that's giving credit to our colonialist cousins, because they didn't. In fact, there were many public meetings where members of the population were actually quite offended that somebody who had been such a key Nazi figure was being showered with public funding, even if it was for the benefit of national defense. So he was slightly persona non grata and working away in the background for some years after his arrival in the States. And it wasn't really until the space race really got going with Yuri Gagarin's first manned spaceflight that von Braun was essentially brought back into the cold. And from that point on, he could do no wrong, and he was given whatever he needed. And You know, to give him credit, he was a very leading figure in the development of a series of rockets, which obviously culminated with the Saturn V, which put men on the moon. And you know, I wouldn't want to detract from his achievement there, but it just goes to show that, you know, you don't necessarily being a good human being and being an effective engineer are not necessarily the same thing. Korolev, on the other hand, I would say had a much more clear-cut moral compass. He was just a very good engineer. He was a very good organizer, and he was very good at getting what he wanted from the Russians as well. He almost went the opposite way to von Braun in some ways, in that he developed the R-7 missile, which was the Soviet Union's first liquid-fueled intercontinental ballistic missile. Now, the Soviets had a disadvantage in that their warheads were much heavier than those of the Americans, and therefore they needed a much more powerful missile in order to throw it. Therefore, Korolev developed a missile that was powerful enough to do that, but he knew full well when he was doing that, that this missile was also powerful enough to, for example, launch a human into orbit, which is exactly what they did with Yuri Gagarin with a slightly modified R-7 missile. And that original design that Korolev came up with in the mid-1950s is, as we shall see, essentially still in use today. He got it right. If we look then at the development of rockets, we can see that on the left here we have the V2 rocket, which, as I mentioned, was von Braun's brainchild. The V2 rocket was an impressive piece of engineering, and we'll look at it more in future slides. However, as a weapon system, it was essentially useless. And again, I'll mention that a bit more later. The center picture here, 1962, we've got a Titan II intercontinental ballistic missile. These were liquid-fueled, silo-based ICBMs from the United States. They were pretty powerful rockets that could put a nuclear warhead essentially anywhere in the world in short order, and they were in service for a long period of time. They did have a few issues, not least fueling, and at least one of them exploded quite badly in its silo, but you know, they were built. On the right here we can see a launch from Kazakhstan of a Soyuz launcher. These were a development of the R-7 missile that Korolev originally designed, and it was this series of rockets that essentially defined modern rocketry. They're still the only means of launching people into space. They are still in service. They've had more launches than all other rockets combined, and they've had very, very few failures. Unfortunately, some of them have failed, but compared to anybody else's rocket, their reliability is exceptional, and a real testament to how good Korolev's team was in that they got it that right that early on. Which is why I have left the very same picture on the second slide about the development of rockets, because Soyuz rockets in upgraded form are still being launched. They are still supplying the International Space Station, and they are still taking astronauts to and from the International Space Station. These things have been in service since the 1960s, and there are no signs of them being retired anytime soon, at least not from the Russian side of things. It may be that they'll be eclipsed by more modern developments, such as SpaceX here in the middle, who have come up with a very impressive stream of launch platforms over the last few years and have been incredibly innovative in a way that I don't think has occurred since the early days of the space race. And certainly SpaceX's team deserve a lot of credit for what they've come up with. For example, here on a Falcon 9, this is two external liquid-fueled boosters, which are similar to the central engine. These have the option to be reused, as in they can actually detach from the rocket once they've burned out and have enough fuel left to vertically land. Now, obviously, that means that the payload is reduced, but it does also mean that the launch cost is reduced. So depending on what the requirement is, whether it's high payload or low cost, you have the option of reusing those boosters, which is, if you have seen them landing autonomously, very, very impressive. And as I say, SpaceX deserve an awful lot of credit for what they've been able to do. Here you have a computer-generated image of a single-stage-to-orbit craft, in this case from a British company. It's called Skylon. Company that came up with it is called Reaction Engines. It's a computer-generated image because if I'd showed you this 20 years ago, it would have been a computer-generated image. And if I'd showed it 40 years ago, it would have been a hand-drawn image. And if I show you it in 20 years, it will probably still be a computer-generated image because single-stage to orbit reusable spacecraft are a unicorn almost that everyone has been chasing for a very long time, and the economics and engineering do not yet work out because it is just not an easy thing to build something that can take off under its own power, maybe horizontally as this Skylon was designed to do, reach orbit, land, and then do it again. Spaceflight puts an enormous amount of stress on the structure. If you want to reuse it, you have to build it heavier. Re-entry is very severe. The craft is likely to have to be completely rebuilt after every re-entry that it does, and currently it just is too much trouble. It looks cool though, so I put it up there. As I said, let's look at the layout of a liquid-fueled rocket. Now, here I'm going to use the V2. This is von Braun's rocket from 1944 because it's a perfectly good example of a liquid-fueled rocket, and it is relatively easy to describe. As described on the main drawing, it has two tanks. It has a fuel tank and an oxidizer tank. The fuel on von Braun's rocket was actually alcohol, which was widely available. The back end here, we have the turbo pumps and the engine. And then there were some changes to von Braun's rocket that are different from what you would see today. It's worth noting that the warhead at the end of the rocket here contained only 1,000 tons of high explosive. Now, to put that in perspective, at that time, a typical Lancaster bomber could take 7 tons of explosives, and later Model 1s might even be able to take a 10-ton bomb load. A Lancaster bomber, even then, even with their short lifespans, would probably last for 3 missions, had a life expectancy of, say, 3 missions. So that would be 15 to 20 tons of explosives over the course of that Lancaster bomber's life. The V2 could drop 1 ton of explosive over the course of its life. However, the V2 cost 2 or 3 times more than a Lancaster bomber. The entire V2 program cost something in the region of 50% more than the Manhattan Project. So the Manhattan Project was the project from the Allies. I know the Americans would claim it as their own, but it was actually a continuation of a British project called Tube Alloys, where they developed the atomic bomb. So this was not a couple of people tinkering around in a basement. This was a significant part of the German economy that went into building this fairly useless weapon. In many ways, it's a good thing that they did, because they put so much resource into it that they had a lot less resource to use on weapons that might have actually prolonged the war. Not to mention the fact that the majority of V2s failed in flight, and those that did hit their targets generally could only hit area targets. So it wasn't particularly useful as a weapon for the Germans. It was arguably a much more useful weapon from the Allied point of view because of how much resources it took. There were some differences with what you might see today. The guidance system was at the front, but the guiding system used graphite rudders which were embedded in the back of the rocket engine in the exhaust. And also, because it was an atmospheric rocket, it used aerodynamic rudders as well, particularly to guide the rocket once the engine had cut out and the rocket was on its more ballistic trajectory. Now, every other rocket since has actually gimbaled the entire rocket motor for a number of reasons. The fins in the rocket exhaust obviously detract from the flow of the rocket, and the graphite can wear out due to the high temperatures involved. Another difference with the V2 versus many modern rockets is the turbo pumps were driven by a separate chemical reaction. I can't remember the exact form of chemical, but it was expanded over a catalyst which created steam, and that drove the turbo pumps independently of the main fuel supply. The other thing that was different about the V2 from modern rockets was its shape. It At that time, don't forget, there had been no manned flight above the speed of sound. Now, okay, they did know that certain types of bullets went faster than the speed of sound. And so the V2 was actually modelled on a shell that was known to be stable in supersonic flight, and that's why it is the shape that it is. Subsequent developments in aerodynamics mean that that is no longer required, and modern rockets can have a much more simple tubular shape. Let's look at a modern multi-stage rocket. I say modern because we're going to go back to our old friend the Soyuz. Feel free to pause the video and have a look around the different parts of it. But a multi-stage rocket is something that I probably should have mentioned earlier. There is no point in launching one large rocket into space. A multi-stage rocket essentially only carries what it needs to carry at the point that the engine is running. So the idea is that you have a first stage, which is here in purple. These take the rocket off. After a couple of minutes, they've burnt out. There is no point in dragging the rest of the structure, all the rocket engines, all the fuel tanks and everything in that first stage up with you, because it's dead weight. You don't need it. So you release that stage, that falls away. And that's what's happening here in this picture. This is called Korolev's cross because the 4 boosters on the Soyuz separate quadrilaterally, and they fall to the ground. So at that point, the second stage, which is the green part, that ignites, and that pushes what's left of the rocket up higher. When the fuel in that stage is gone, it separates from the pink stage at the front, and then the pink stage only has to push the payload and its own fuel up. So basically you're shedding structure as you go up, and don't forget that the structure is 6% of the rocket. So if you've got, say, 2% mass in dead weight, that can be very, very significant. So a staged rocket is designed to basically make the best out of a bad situation. In principle, an infinite number of stages would be best. Some means of basically dropping each stage individually, but that doesn't take into account the fact that the engines themselves and the fuel systems have mass, so you know that wouldn't work out. So most rockets usually have 2 or 3 stages. 3 is very, very common, and Soyuz is no exception. The different stages will often use different rocket engines and will often have different fuels, but that again is a little bit more complex than I'd like to get into today. To separate the stages from each other, explosive bolts are generally used. That is literally what it sounds. It's a bolt with an explosive charge in the middle. So you do the bolt up to connect everything together, and then when you want to separate the charge, you blow the bolt and everything fires away. If we take a quick look at a modern a modern liquid-fueled staged combustion diagram. This isn't any particular engine, this is just a engine. At first glance, it may seem a little bit complicated, but it isn't really conceptually too complicated. What we have here is turbo pumps. Now, the pumps are needed to pump the fuel from the tank into the nozzle where the actual combustion takes place, because don't forget the pressure is very high when the combustion takes place, which means that the pumps have to pump the fuel in at a pressure that is much higher than the combustion chamber pressure. Otherwise the combustion would just work its way back up into the fuel tanks, and not to put too fine a point on it, kaboom. The pumps are driven by turbines, similar to aircraft engines actually, and the turbines are supplied with fuel and oxidizer. On this instance, in this engine here, we have 2 pumps. The pump on the left of the screen is the fuel pump. Fuel is pink. The pump on the right of the screen is the oxidizer pump. Oxygen is blue. The pumps are at the bottom of this assembly here, and the turbines are at the top of the assembly. We also have some low pressure pumps, but I'm not going to mention them. They essentially work in a very similar way to what I'm about to describe. What happens is the fuel, which is pink, enters the top of the pump chamber where it's mixed with some oxygen. This comes from the low pressure pump. Then it's combined and burned. That creates a gas flow that runs past these turbines. These turbines spin the pumps, and those pumps pump oxygen into the combustion chamber. On the fuel side, a similar thing happens. Fuel and oxygen enters the pump, which is burned, and spins the pump. Now, you'll notice that actually the fuel does not go into the combustion chamber directly. What actually happens is that the fuel pump pumps more fuel into the pumps, that both the fuel pump and the oxidizer pump, than they actually need. So both these turbos run in a very fuel-rich manner. And there's a number of reasons for that, but one of them is that running it in an oxygen-rich manner would basically melt the pump. So they're run in a very fuel-rich manner, and what that means is that although the oxygen pump pumps the oxygen into the combustion chamber, the fuel pump doesn't. It pumps the fuel through the turbos, and then the exhaust from the turbo, which is very fuel-rich, goes into the combustion chamber, and that is where the ignition takes place, and the hot gases come out of the back of the engine. Now, obviously, there's quite a lot more to it than that, and I haven't really done it justice, but the general concept is that you pump fuel and oxygen into the combustion chamber in some manner, and different engines do it in different ways. This way is a multi-stage combustion system. Obviously, it's nothing like that simple in practice. Here again is a picture of what I believe is a space shuttle main engine, and you can see it is a mass of pipes, wires, gauges, bolts, I don't know what, and that's just one part of it. Again, similar to aircraft engines, engineers have designed the simplicity out of these things in order to get the absolute maximum performance possible from them. And there is nothing about them that's simple, not the materials, not the control systems, not the feeding systems, not the plumbing, nothing. It's not simple. But it looks simple when you see it on a diagram like I've just showed you. There are significant limitations to chemical rockets. So although chemical rockets are the only type of rocket that we generally use, there are a few ion thrusters kicking about on certain satellites, etc. They do have quite severe limitations. They cost a lot of money, as we've seen, not just the engineering of the rocket itself, but the fuel, the infrastructure, the ground launch control systems, and so on. They don't have a very big payload, as we've said. It's about 4% of the total all-up mass. And oddly enough, they're relatively slow. Now, they're not slow in comparison to your Ford Escort, but they are slow in comparison to anything that we might wish to achieve if we ever wish to truly leave the clutches of the little green ball that we currently live on. On the right here, you can see the speeds of extra solar system probes. So Pioneer 10, 11, Voyager 1, Voyager 2, and New Horizons. These are the only probes that have actually gone to the edge of the solar system and are continuing. Now, they are all traveling in the region of 50 to 60,000 kilometers per hour, which obviously sounds very fast because, you know, I mean, my first car only lasted for about 180,000 kilometers before it disintegrated. So that would take one of these space probes about 3 seconds. So to me, very fast. To, for example, light that travels at 186,000 miles, that's 300,000 kilometers every single second, we are not even in the same 5 orders of magnitude. And it takes light 4 years to get to the nearest star, which means that it would take Voyager 1 20, 30,000 years to get there. And unfortunately, that's just not fast enough for our needs. So we really do need to come up with some way of improving things. There are a number of concepts that look promising, but at the moment there doesn't seem to be an economic drive to actually develop those concepts into something that might work in practice. But here's hoping. So I'm going to end it there. Thanks very much for watching. If you do have any questions, feel free to put it in the comments box below and I'll get back to you. Also, I'm aware I may have made 1 or 2 errors, so don't be afraid to point them out and let me know what you'd like me to talk about next time, or if anything. And enjoy the rest of your day. Thank you.